Today we're going to start looking at this basic area of actuarial math. So we're going to be looking at interest rates, which can be expressed in 4 different forms. Then you'll see the sort of connected topics where you've got the sum of multiple cash flows, where you've got the force of interest. This is a very powerful concept, e to the minus whatever the force of interest is, and that can be variable over different points of time, and spot rates and forward rates and the yield curve. But we're going to start with the most simple stuff, the different 4 ways of expressing interest rates. So those 4 methods we have, and they all basically describe the same thing. That's the really key thing here. So I, V, delta as it should be written, and D all basically express the same thing. So the one you're probably most familiar with is I. So if you, for example, got £50 in the bank and you're getting 4% interest, you can probably work out how much money you're going to have. So okay, so if you start with £50, you get 4% per annum. How much do you have at the end of the year? Okay, well, let's take it through very slowly. 4% of £50 is equal to £2. Okay, because that is 4 over 100 times 50, if you really want to slow this calculation down. Okay, so at the end of the year, we've got £52. Okay, so what you might notice is what I've done there is 50 plus 50 times 4 over 100. Okay, which factors out to 50 times 1.04. And this is the first really key way of thinking about things. Instead of sort of working out how much interest there is and adding the interest on, we just multiply by this thing, which is really 1 plus I. The way to think about that is it's 1 plus I, 1 plus the rate of interest. Now if I leave my money in the bank for 2 years, okay, then I've got 52 plus 52 times 4 over 100. Okay, or in other words, 52 times 1.04. Well, 52 is 50 times 1.04, so that is also equal to 50 times 1.04 squared. Okay, which happens to be 54.08. Okay, so that's great news. We can now see how this whole thing is going to extend. And if I've got, say, £50 in the bank for 10 years, then it's simply 50 times 1.04 to the power of 10. Okay, which is equal to 50 times 74.01. We can also do fractions of years. So if you've got your money in the bank for 6 months, then at the end of those 6 months, assuming the interest is continuous, you're going to have 50 times 1.04 to the power of a half, which is going to be a bit less than 51 because it's compound interest. Okay, it's going to be 50.99 because 50.99 times 1.04 to the power of a half is equal to 52. Okay, so you can see you can do it multiple years, and you can also do it part years. I mean, you could do it for 3 months by taking to the power of a quarter, etc. So that's how we do the basic continuous interest calculation. And what we now need to look at is a concept called present value, where we turn the thing round and we say, instead of having £50 now, and how much are we going to have in the future, we say, if we're going to have £50 in the future, how much is it worth now? Or in other words, how much do we have to put in the bank now to have £50 in the future? Okay, and this is particularly relevant because in life assurance and in pensions, we promise certain amounts of money in the future. Okay, so we need to know how much money do we put in the bank now in order to have that amount of money in the future. Okay, and that is a concept we call, that is a concept we call present value. Which we usually just write as PV. Okay? So the question is, if we receive, say, £200 in 5 years, and I is equal to 6%, what is the present value? And it's just algebra now. We just solve this algebraically. So we don't know what the present value is. Okay. So let's just call that PV. Okay. But if we put that's how much money we need to put in the bank now to have £200 in 6 years' time. Let's just bring that down so we can see it. So in 5 years' time. So we do present value times by 1.06, because it's 6% interest, to the power of 5 is equal to 200. Okay, so what that equation is going to allow us to solve is how much money we need now, so that it will be £200 in 5 years' time at 6% interest. And then it's just algebra. So the present value is equal to 200 over 1.06 to the power of 5, or 200 times 1.06 to the power of minus 5. Hopefully you realize that's not the same as 0.94 to the power of 5. Okay. So what is that? Well, that's fairly easy now to work out. Equals 200 times 1.06 to the power of minus 5. That is £149.45. Okay, so that's how we work out present value. Okay, so in general, the present value is equal to the cash flow divided by 1 plus the rate of interest to the power of the term, of the time. And if you think about it, if you're due to have £200 in 5 years' time and another £200 in 7 years' time, that your total wealth is the sum of those two. So we can't just do one calculation like that. We can actually calculate multiple cash flows in this way and reduce them all to one present value, which is really quite a powerful concept, because it means instead of thinking about all these different cash flows in the future, we can convert them all to the current time. So C1, the first cash flow, 1 plus the rate of interest times the first period of time plus the second cash flow over 1 plus I to the second period of time plus etc, etc, for all the cash flows. So we've got n cash flows, 1 plus I to the t subscript n. So we can take a present value of an entire stream of cash flows arbitrarily far out into the future. So that is how we do those sorts of questions. That is how we work out what the present value of a cash flow is. And T1, T2 here could be any period of time, so it could be 1 month, 2 months, 3 months, etc. It could be 5 years, 10 years, 30 years, something like that. So it doesn't matter what those periods of time is, this piece of mathematics always works. So that brings us on to the next issue of what are all these other letters. So we introduced all these letters at the start. Okay, I, V, delta, and D, and they're all just different ways of describing the same thing. So if you understand it in terms of I, there's really nothing left to understand about the concepts here. Okay, so I'll just give you what these definitions are. Okay, so the easiest way to express this is to write 1 over 1 plus I, because that is your basic, that's your fundamental sort of discounting factor. That's how you reduce your present value in the future. Okay, and that, well, the purpose of V is that is simply equal to V, which is really just to save you on the notation. So there's a bit of a faff to write over 1 plus I to the power of T. Okay, so you can just write V to the T instead. Okay, that is also equal to E to the minus delta. Okay, the reason for this is it's just E just works very well with continuously compounding numbers for the very simple reason. I'll just do it as an aside. If I do 1.01 to the power of 100, then I do 1.001 to the power of 1,000, then I do 1.00001 to the power of 1,000,000. Okay, this thing eventually tends to E. So E has very nice properties in terms of compound interest and that sort of thing. So that's why we use E, but it's just an algebraic definition. At the end of the day, E to the minus delta is equal to 1 over 1 plus I. Okay, and the other one is 1 minus D. Okay, so all these things are equal, and that's all you have to remember about what these numbers are. Because you can just use them interchangeably. The purpose of D is it's how much you take off an amount of money to reduce its value in the future. Okay, so if I is say 6%, 1 over 1 plus I will be about 0.942 or something like that. Well, that means D is 5.8%. Okay, it's the amount you take off because the money is paid in the future. This is far less frequently used. Okay, so the really important one to understand is what 1 over 1 plus I is. Then we'll see, using the force of interest later, it's quite a powerful thing for the more continuous type of mathematics, and V just enables us to reduce the notation. Okay, and then once you've got this relationship, okay, you can just manipulate them quite easy. So we say, well, what is delta? If I know what, if I'm given I, what is delta? Okay, well, I just rearrange this formula. So 1 over 1 plus I equals E to the minus delta. So log 1 over 1 plus I equals minus delta. So plus delta equals log 1 plus I. Okay, because log 1 plus I to the minus 1 is minus log 1 plus I. Similarly, if I want to get I in terms of delta, just rearrange it. So 1 plus I is equal to E to the delta. I equals E to the delta minus 1. And I can easily get any form of interest from any other, and all I need to remember is this set of formulas here. And you'll just get used to using V when it's appropriate to use V. Okay, so that is what I, V, delta, and D are. We will do a more numerical example in the next lecture, which is going to be on the summation, so the sort of automated way of doing summations. But for this lecture, it's really just a matter of getting you used to what I is, what V is, what delta is, and what D is, and what the concept of present value is.